talking about geometric phases for Neumann algebras and ADS-CFT.
Yes, thank you very much. So thanks a lot for this kind invitation to this very nice conference, and I'm extremely happy to be here. And so I should just briefly mention that Wuerzburg is a university town in the north of Bavaria, and here you can see one of the several castles that we have there. So my talk is devoted to some particular aspect of the ADS-CFT correspondence as is appropriate for this workshop. Sorry, what do I have to do? Okay, sorry. And so the aspect of ADS-CFT I'm going to discuss is this relation between geometry and entanglement that follows from this duality. In particular, following the celebrated Ryo-Takayanagi result relating the length of a geodesic in ADS-3, for instance, to the entanglement properties of field theory. And so one particular example that I'm going to consider are wormholes as related to eternal black holes, and also the question of factorization of Hilbert spaces. And so I will do this both for simple systems in quantum mechanics, but then also for more involved examples in the context of ADS-CFT. So in the title there's this word geometric phases, and so another word for geometric phases is actually Berry phase. And so I discuss these Berry phases both in just simple quantum mechanics system, but then also in the context of ADS-CFT. And so it shows that this is a nice mathematical concept that is both realized in simple quantum mechanical systems, and it may also actually lead to new experiments that are motivated by some aspects of ADS-CFT, so I'll mention that also. But on the other hand, there are also these a lot more formal aspects, in particular the relation to the so-called von Neumann algebras that I briefly introduced for you. And so while most of the talk is really about quantum mechanical systems, in the second part I will also turn to two-dimensional conformal field theories and their gravity duals in this context. Okay, so let me motivate further why it's interesting to look at Berry phases for wormholes. So as I already mentioned, the wormholes are also an example that provide a relation between entanglement and geometry in the ADS-CFT correspondence, and I'm studying this particular relation here, so this is a kind of prototypical example. And I'm also going to refer quite a bit to some very nice papers of Hermann Verlinde, who is actually also here, and who actually showed to us that this concept of a wormhole is also present already in very simple quantum mechanical systems, and I will show you briefly how. So in particular, the Berry phase provides a geometrical picture of how actually degrees of freedom entangle in particular quantum mechanical systems. And so this can be used to study, for instance, the so-called factorization puzzle, so which in short is that if you have two CFTs that are not interacting, then they should have a Hilbert space, which is just the product of the two Hilbert spaces of these two CSTs. However, if they actually are located at the two sides of an eternal wormhole, then on the gravity dual side, you should just have a non-factored Hilbert space, and that seems to be contradicting the proposals of ADS-CFT. And at least with the means that I'm presenting here, we will have a very good tool to quantify and to analyze this puzzle. And so actually, this is in the context of geometric quantization, so it's really, from the mathematical point of view, it's a fiber bundle approach. And okay, I won't go into many details of these mathematical structures, but they are clearly behind everything that I'm going to say. And also, they provide a very nice way to quantify the missing information that is associated to entanglement and entropy, and so show how this information is actually quantified in this geometrical context. So then the von Neumann algebras, they have been studied recently quite a lot in the context of the ADS-CFT correspondence. And so actually there's a classification of these algebras that show to you how to define a trace in a given operator algebra. And so one of the main results that I'm going to show to you is that this definition of a trace actually requires these Berry phases to vanish. So I'm going to explain that in quite some detail. And so while I explained that in quite some detail for a quantum mechanical system, it also applies to ADS3 CFT2, so in one dimension higher, and I'll comment on that as well. Okay, so here's just a list of the papers that I'm going to use that I used to prepare this talk. So on the Berry phase in quantum mechanics and wormholes, this was actually some work of our group in Wuerzburg together with two condensed matter colleagues in Dresden, Flavio Nogueira, who I think originally he is actually from Sao Paulo, so he's now in Dresden, but I think he's from Sao Paulo, and Jeroen van den Brink, who is also a condensed matter physicist, and so then there's René Meyer, my colleague, and students and postdocs like Shrovik Banerjee and Moritz Dorband. And in the second paper, we went one dimension higher and did it in AD3 CFT2. So it's the same crowd in Wuerzburg, but also my student Annalena Weigel. And in this recent paper, this is also again the two students and Shrovik Banerjee, where we relate this to the von Neumann algebras. So Annalena is going to submit her PhD thesis next week, so I still have to read her thesis before I get back. Okay, good. The first topic I'm going to turn to is to give a brief review of black holes, wormholes, and ADS-CFT, and the factorization puzzle. So that will just be a few short slides to set the scene of where we are going. So the idea is to consider an eternal ADS black hole with the diagram given here in global coordinates, so in cross-scale coordinates actually. So this has two sides, and there's a left and a right side. Note that in one side the time goes in this direction, and the other one the time goes in that direction. That will be very crucial actually further along. And so here's the eternal black hole with a horizon, and it's actually a non-traversable wormhole, which means that observers can move in from the two sides, but it's not possible to get out again on the other side. And so what will be very important for this geometrical approach is that there's actually a singularity in the time coordinate, which is that the time-like killing vector switches sign at the horizon. So if one observer hops in from this side and another one from the other side, their killing vectors will point in different direction, and this is clearly a singular behavior. Okay, so as proposed by Juan Maldacena already in the early days, I would say, of the ADS-CFT correspondence, we can view this eternal black hole in these global coordinates in ADS space-time to be dual to two copies of the boundary CFT. And so there's one CFT is on the left-hand side, the other is on the right-hand side, and they're actually entangled in the so-called thermophile double state. So a thermophile double state is the purification of a thermostate of one CFT. So you have one CFT with a basis, say, the right-hand side has this basis here. And then, this is a concept much older than ADS-CFT. Then you just write down a different copy of the CFT and define the state. And then this actually gives you a pure state. But the point is that if you take now a partial trace over one of the two sides, then you return to the thermal density matrix of the other one. Okay, so another important development, which goes, I think, essentially back to Van Armstrong in 2010, and also Maldacena and Susskind, is this ER is equal to EPR proposal, which is, as we will need for this talk, a relation between entanglement and geometry. And so EPR stands for the Einstein-Podolsky-Rosen entanglement, and ER stands for Einstein-Rosen bridge, which is essentially a wormhole. And so the idea is that two entangled CFTs with EPR correlation are connected through a wormhole, so this Einstein-Rosen bridge. So the blue line is actually a geodesic in this geometry, and the red line is one where a particular symmetry transformation has been applied, and this will play an important role further on as well. Okay, so also let me briefly explain this factorization puzzle. So the two CFTs have disjoint Hilbert spaces since there is no interaction between them, and so you should have such a product structure for the Hilbert space. But on the other hand, the wormhole Hilbert space, so this is just one wormhole, so it has one Hilbert space, and there's no obvious reason why this should factorize. So there's an apparent contradiction, but actually recently there was quite a lot of progress on understanding what's actually going on. And certainly what I'm going to show you here, these geometric phases, they will also be helpful for actually formulating in this puzzle in a quantitative way, which is, of course, a big step towards really understanding what's going on. Okay, and as I mentioned, another important ingredient is this work by Hermann Verlinde, who is there. And so he studied simple wormholes in quantum mechanics, and so the upshot here is that if this is the partition function for a thermal system with a quantum mechanical Hamiltonian, then actually, so there's this whole machinery of analytical mechanics due to Arnold, and for instance, that implies that if we now consider generalized coordinates and momenta, so we are in phase space, we have coordinates and momenta xa, then there's a symplectic form which takes this particular form here. So this is for any dynamical system in also already in classical mechanics. And the point is that the partition function can be written as a path integral over the disk, so this geometry here, over all of these coordinates of the phase space. And so there's one term that involves the symplectic form, and then there's a boundary term here over the thermal circle, which involves the Hamiltonian. And now one upshot is that if the symplectic form is exact, which means that you can write it as an exterior derivative of some other form, then you can use Stokes' theorem. And then actually the path integral over this manifold reduces again to this partition function that we have here. But the much more interesting thing, and that's what we're actually also going to consider in detail here in this talk, is what happens if the symplectic structure is non-exact. Because if it's non-exact, then you can't use Stokes' theorem, and this means that you have to stick with these extended integration regions. And so if you calculate the accumulation function of a partition function here, for instance, with 4 of them, so this n would be taken to be 4, then actually your integration region has this wormhole structure. So here already is a multi-mouth wormhole that you can get in this way. So this kind of wormhole-like structures also just arises as an integration region in a quantum mechanical system. So that's essentially explained in great detail in this paper. All right, so that was my review part to set the scene, and now let me turn to these geometric phases and what they tell us about the story. So, first of all, let me briefly define what a Berry phase is. So, actually, there's this very nice review in the lectures by David Tong on the quantum Hall effect. And so this is an ubiquitous mathematical concept in all branches of physics, in particular in condensed matter physics. There's a lot of use of this. And so just at the level of a quantum mechanical system, if you start from the time-dependent Schrödinger equation, which depends on a certain set of parameters called lambda here, then you can write the ground state as the time evolution of some basis with some set of unitary operators that depend on time. And then you can define the so-called Berry connection. So it's a connection in a mathematical sense of covariant derivatives, which actually has as components so if you have several of these parameters lambda, then you act with the derivatives with respect to these parameters on your basis states, and that defines this connection. Now, inserting this ansatz into the Schrödinger equation, then you get this equation for the time evolution of U. And the Berry phase is then this path exponential path integral in the sense that it's it's an integral along a closed path in this space spanned by the lambdas. And so that actually defines a phase. And here, this is one of the simplest things you can do is just to consider one spin-and-a-half particle in a magnetic field. And so if you wrap this, if it's you can take electrons and you wrap them once around this magnetic field, then you get something like this. So this picture is actually in the space spanned by the 3 components of the magnetic field. And that will then give rise to your Berry phase. Okay, so now what will be important if you want to go to higher dimensions is that you can also write this in a much more mathematical language. And so you can actually write this for a connection for a group manifold, M. And you can define the so-called Maurer-Cartan form for any group element sigma. So, I mean, that includes the previous example, but it's much more general. Okay. And then the Berry connection, if you still look at quantum mechanics, will be the ground state expectation value of the so-called of this Maurer-Cartan form. So here, so psi naught will be the ground state of some quantum mechanical system. And then you can also define a Berry curvature taking the exterior derivative of this connection. So this is called the Kirillov-Kostan symplectic form in the literature. And again, then you take this expectation value with respect to the ground state, and the Berry phase is then, because you have a 2 form here, you can consider putting a sphere around it, and then this again gives you the Berry phase. So this is a very mathematical definition which encompasses the simple quantum mechanical example that I was mentioning before. Okay, so, and I will show you that these Berry phases actually have a very important role in the context of the so-called von Neumann algebras. So before I go into what the relation is, let me just extremely briefly review what a von Neumann algebra is. So it goes back to the Hungarian mathematician and physicist Johann von Neumann, who's actually, he did an amazing variety of different things in quantum mechanics, mathematics, and lots of fields. And actually, this original proposal already comes from 1930. I'll show you his original paper in a minute, and you can almost say this is almost already 100 years ago. So it's very impressive that he thought about these things very early on, even before quantum field theory, and even when entanglement was not really well developed yet as a concept. In the context of ADS-CFT, this has been studied over the last, say, 2 or 3 years quite extensively. I think there's a very early paper by Robert Jefferson, and then Liu and Leutheusser, and also Witten and Chandrasekaran and Pennington made important contributions to this very recently. So what are these von Neumann algebras? Well, it's a concept of algebraic quantum field theory, which can be used for classifying operator algebras with respect to their entanglement properties. Okay, and this classification has 3 types, essentially type 1, type 2, and type 3. Type 1 is the one that you have in quantum mechanics, so I will talk about this quite a lot as an example for quantum mechanical systems. So if you have a finite dimensional Hilbert space, and so these for Neumann algebra, first of all, it's an operator, it's an algebra of operators that act on a particular Hilbert space. And in this type 1, there is actually, these algebras of type 1, they admit irreducible representations of this algebra, and that actually allows you to define or write down a well-defined expression for a trace functional. So a trace means essentially a functional which is cyclic in its arguments. And then, of course, that also allows you to define a density matrix, and then the density matrix is essential for writing down the von Neumann entropy. So that's the relation. And so that's the typical situation in quantum mechanics. Now, there's 2 other types which are more relevant if you want to study quantum field theories and also black holes. So the second easiest to understand is type 3, which means that there is no such trace prescription, and that applies, for instance, for free to free quantum field theories. So what's happening in that case is that there is no irreducible representation of this algebra, and so then essentially you can't write down what the density matrix is. So in terms of the von Neumann entropy, if you write it for quantum field theory, even for a conformal field theory, you always have this need to regulate. You have to introduce a regulator, and that's so. Of course, if you take the regulator to infinity, then you don't get a meaningful expression, and that's exactly what is meant by these type 3 algebras. And then there's this intermediate type 2. So where again it does not act reducibly, but there are particular states, and in particular the maximally entangled states, that allow you to write a trace description for this particular chosen state. Okay, so that's the classification, and I will show you the relation to this Berry phases in a minute. Okay, just for some fun, I actually found this original paper of von Neumann, which is from 1930. I think it was written in 1929, but it took a year till it got published, and it's in this. It's actually a Matz paper. Okay, I don't have the time to translate to you now, but if you're interested, just ask me afterwards. And actually, if you so Einleitung, this means introduction. Okay, and so the things I explained to you on the previous slide actually already appear in this. The battery is flat of the pointer. Actually, do you have a? Sorry, do you have another pointer? I have the finger in front. No. Okay, there it is again. Sorry, yes, okay. All right, so essentially what I just told you on the previous slide is already encompassed in, no, it's really dying. I don't have my finger. I have a pointer myself, actually, if you, let me get my pointer. Sorry about this, I think it would be useful. I will use this one. Okay, so thank you. Okay, so essentially what I just said on the previous slide is encompassed already in this first paragraph of the introduction, and so it's interesting that he talks about so-called normal operators. So, and by normal, he means those operators of type 2 and type 3. So because he says, in quantum mechanics, essentially we look at those, but they are very constrained, and the more general ones are those. So, and it's interesting that the more general ones he actually calls the normal ones. I think that's very interesting. All right, okay, so this is of some historical interest. So it's really already quite some time ago, so if you are interested in getting a translation, ask me afterwards. Okay, so now let's apply this to the simplest possible case, which is just 2 spin-1/2 particles. And I'm going to show you for this very simple example, but very explicitly, how the Berry phases and the type 1 von Neumann algebra are related to each other. Okay, so no. God. So this one looks. Okay. Yes. So I'm going to consider a system, also a Hamiltonian, that describes 2 coupled spin-1/2 particles to 2 electrons in an external magnetic field. But so here, this is my very simple Hamiltonian. So we see these 2 spins, they interact with each other with a coupling constant J. And then one of the 2, okay, so it means we can consider the spins as being a nucleus, and also a proton and a neutron in a hydrogen atom. And so only the electron is going with the magnetic field. Okay, so this is a very simple Hamiltonian for which you can write a Berry phase because you can wrap around this magnetic field. Okay, so then you can solve the Schrödinger equation for this Hamiltonian, and then the ground state is given by this expression here. And so please remember the definition of this alpha, because alpha is related to both the magnetic field and the coupling constant. Okay, so now you can consider the Hilbert space of this model, which is in principle is SU4. But then you can restrict to the so-called projective Hilbert space, which removes all the phases of physically equivalent states. And so essentially, this boils down to the state of the space of all the pure states. And then in quantum mechanics, there's also something called the Schmidt decomposition, which means you can write the ground state here as a sum over tensor product from the Hilbert spaces of the 2 individual theories. And here, if you do this, you get 2 coefficients. That's related to what I was writing here, and they look like this. So alpha is related to the magnetic field divided by the coupling constant. So this is the coupling constant, here's the magnetic field. Okay, so Then you can write down the entanglement entropy, so essentially, which is the von Neumann entropy for these two subspin stems, and you can just calculate it explicitly from the Schmidt coefficients, and it looks like this. Again, alpha involves both the magnetic field and the coupling constant. And now there's something interesting, which is called an entanglement orbit. And so an entanglement orbit is a subspace of the Hilbert space where the entanglement entropy has the same value. Now, if the coupling constant is 0, then also the entanglement entropy is going to be 0. And then you can show that this entanglement orbit will just be the product of the left and the right Hilbert space. So you have one Hilbert space for one spin and the other Hilbert space for the other one, and they just form a product. Okay. I mean, already you can see the relation to the black hole case in ADS. So you have the left and the right CFT, and if they're not interacting, then I mean you get such a product structure. Now, if J is very large for finite magnetic field, then you have maximal entanglement, which in the simple case means that the entanglement entropy is logarithm 2. And then you can actually show that this entanglement orbit doesn't factorize anymore, and it's actually an RP3, which is SU2 divided by Z2, because so Z2 is essentially exchanging the two spins. And so this is, if you have these experiment with teleportation for a maximally entangled state, if you measure one state here, then you know exactly what the other state is going to do. And so that's why the Hilbert space takes this much simpler form. And then there's lots of intermediate values for different values of this alpha. So I think this is for alpha pi half, and this is for alpha is equal to 0. And then you get intermediate states where you have a product structure, but this here is much more involved than the CP one that we had before. Okay, so just to summarize, we look at this projective Hilbert space. There's a factorized subspace which just corresponds to two single qubit subspaces that don't interact with each other. So if there's no entanglement, then the ground state lies in this factorized structure. And then on the other hand, if we have maximal entanglement, then the states are in a non-diagonally embedded submanifold of this projective Hilbert space, which is actually RP3. Okay, so and now I can actually relate the Berry phase for the system to the type 1 von Neumann algebra. So the Berry phase I actually get from the symplectic volume of this entanglement orbit. Okay, so I use this differential geometric structure. So I just pick one representative of the orbit, which is this. So the reduced density matrix you actually get as the square of this P, and then this is a 1 point that defines the orbit, and then you get the other points in the orbit by acting with this unitary transformation with the Pauli matrices, and you see two different angles, theta and phi, that contribute here. And then you can define the connection on the orbit from this map Q, and so you can just calculate what it is, and the symplectic form then is the exterior derivative, so it takes this form. And then, as before, we can calculate the integral over the symplectic form. And because the volume form, it's not exact, and you get 2 pi sine alpha. And this is our geometric phase. Now, what is going to be very important is that if you have a maximally entangled state, then this geometric phase is actually going to be 0. And that will be very important. Okay, so now what's the relation to the type 1 von Neumann algebra? So we want a trace functional. So this means we want some linear functional with these properties. So this curly A is the von Neumann algebra. So, and we want a particular functional that's cyclic, so that satisfies this relation here. Now we want to define this for our quantum mechanical system. So we take the ground state, the one we calculated before, and take one element of the von Neumann algebra for the left spin, and write a basis using the Pauli matrices. And then we can calculate so if this is our F0, we can calculate this for a commutator, and that's what we have. So that's what we get. And now the point is that the geometric, this sine alpha we already just found here before, is sine alpha is precisely our geometric phase in the simple case. Okay, so now we can invert this relation, and then essentially we see that this trace functional is proportional to the geometric phase. I mean, just using this particular example, very simple example that I showed to you. So what we find is that the trace functional evaluated on this commutator. So if we have this relation, then obviously this has to vanish. And so this trace functional is proportional to the geometric phase. And so if we want this to be an honest trace, it has to vanish, but it only vanishes, as I showed before, if this phi 0 is a maximally entangled state. Okay, so this means only for maximally entangled states can we define the von Neumann algebra, the trace on the von Neumann algebra. Okay, that's an important result, and I will show you how this also is realized in the black hole context. But before I go there, let me quickly say that there's nice connections to experiment, because these are things that can in principle be measured. So let me not go into the details here. I just want to mention this fact that, as reviewed in this paper, for instance, it's possible in some simple quantum mechanical systems by repeated measurements to reconstruct the entire density matrix, and this means that in principle you can also analyze the structure of these entanglement orbits, and I think that would be very interesting to do, just to have a comparison to what happens for the black holes. Okay, so now let's move to ADS-CFT and the black holes. So the lesson here is that you get a very similar structure. So there's actually also a non-exact symplectic form, and consequently there's a non-zero Berry phase. Because actually, as I mentioned before, there is no global killing vector in the presence of a wormhole. And so, in fact, the mass or the temperature of the eternal black hole, they give you this correlation or the difference between these killing vectors. And so, I mean, if, again, we start from this picture and then just look at it from the side and add an extra dimension, essentially what we have is here is our left and our right flat space, and then we have a wormhole. And so for two observers coming from the two sides, they will disagree on the time when they meet. And so the difference between the left and the right time we can essentially call delta. And so this delta will be a particular phase, and which will play important symmetry, have an important symmetry property. Namely, so if we start from this configuration here, we can do two different things. We can evolve by the sum of the two Hamiltonians, and that's actually not a symmetry, so it will just essentially add a phase to our original TFD state that we had in the boundary. But on the other hand, if we evolve by the difference between the two Hamiltonians, that is actually a symmetry, and which does not transform the state that you're considering. And this symmetry, so the parameter of the symmetry will be precisely this delta here. Okay, so to put this into a more mathematical terms, so we have time translations on each boundary. So this is a U1 symmetry on each side. And then there's a bulk isometry for this difference, and so which is another U1. So the bulk modular space of the classical solutions is the boundary symmetries modded by the bulk symmetry, but that's again just a U1, which is a circle. And so now the Berry connection will actually be the winding number if you go around the circle. And so this is a non-trivial winding number. And actually, you can do this explicitly by using JT gravity and do this calculation. And you actually find that this geometric phase is actually non-zero, and it's proportional to the geometric phase of the bulk modular space. Well, okay, let me just go back. Isn't that equivalent? Well, I mean, essentially it's just because you get this phase multiplying your state. So that's because you have e to the I something, so that's why I call it U1. Okay, so, all right, so essentially what we will have here is that, actually in general, we have a type 3 von Neumann algebra, which means that we can't define a trace. and that will be precisely, so the lesson here is that this is related to the presence of this non-exact symplectic form, which leads to the presence of this Berry phase. Okay, so I showed you this simple example for type 1 for Neumann algebras for quantum mechanics, but so now there's this, of course, this very nice recent story for differentiating between type 2 and type 3. Let me just very briefly review this. So here, essentially in all these papers, the idea is to consider single trace operators for a generalized free field theory in the large N limit. And that gives you a type 3 von Neumann algebra. And so the construction applies to each CFT individually, and so, and in fact, both algebras have a trivial center. But then the problem, an issue is if to include the Hamiltonian, which diverges with n squared if you take the large N limit. So this cannot be included into the algebra, and so the idea is, and also we have to regularize the two-point function by subtracting this expectation value. And so then considering this operator U, which is essentially this Hamiltonian divided by n, then if you calculate the commutation relations, and so the algebra, then here using the Schrödinger equation you get this, and so in the strict large infinity limit, this commutes, okay? So, and it commutes with all the operators in the left algebra, okay? So this means that there's no center. But now the idea is to consider this tensor product, which includes the algebra of bounded functions of U. And so now here the key point is that to construct the algebra for the right hand side CFT, the same operator U has to be used. And so again, it means that both the left and right algebra share the same center, and actually the center will be proportional to the black hole mass. And so the statement that's obtained in this context here is extremely similar to what I was telling you using the Berry phases, because, okay, so going back to this picture again, so we say we have a non-exact symplectic form coming from the fact that the time-like killing vectors don't agree, so there's a singularity which gives you a non-exact symplectic form that gives you a Berry phase, and actually this Berry phase will be proportional to the mass of the black hole. And so if you phrase the same statement in this von Neumann algebra language, then what you get is that the center is shared by the two algebras, and which is proportional to the black hole mass. So you see quite a similarity between the two statements. Okay, and then now it's actually possible to take the step from going from type 3. So type 3 is really an explicit large N limit. And so as pointed out by Witten, so if we include now 1/n corrections, then we actually do get a type 2 algebra vanishing center. So remember, type 2 was this intermediate algebra where for particular states you can actually define a trace functional. And the statement can also now be phrased in the geometric phase approach. So if we have non-factorization, okay, so this means that we have a non-zero geometric phase, then we can't define a trace, and then we have a type 3 von Neumann algebra. On the other hand, if we have a maximally entangled state, so in the case of the eternal black holes, that would mean that the temperature goes to infinity. I'm not exactly sure what that means, to be honest. So that really shows that to really make very concrete statements, we have to do something explicit about 1/n, but that's, of course, complicated to do. So for this maximally entangled state, that would be the only case where the geometric phase vanishes. And in that case, we would go to a type 2 von Neumann algebra. Which again means that this potentially leads to a factored Hilbert space on the two sides, and so we would solve the factorization puzzle. Okay, so that's described in this recent paper here. 5 minutes. Okay. So one comment is that this Berry phase approach also very nicely quantifies the missing information. So in particular, when a symplectic form is non-exact, there's no global section for the entire system. So that's expression from differential geometry, which means that essentially you need different coordinate patches to cover the Hilbert space. And so this means that an observer in one coordinate system or one coordinate patch has no information about the other. And that's precisely happening for observers at the two sides of the wormhole. But essentially, you can also have a similar picture if you have just this two-spin system, because again, there due to this non-exact symplectic form, you don't have a coordinate patch that covers all of the S2 sphere that we're considering there. So there again, the mathematical structure is very, very similar. Okay, so in the last 5 minutes, let me give you a brief impression of what happens if you go one dimension higher and you really do this in honest ADS-CFT, and in this case of ADS3 and CFT2. Okay, in 5 minutes, I don't have to go time to go into all the details, so let me just tell you the main message, and then please ask me afterwards. Okay, so in a TFT2, we start with the Virasoro group, which we can essentially write as the diffeomorphisms on S1. So the group elements will be just the functions of the angle on this S1, and alpha characterizes the central chart. Then here's the Virasoro algebra, and then we can consider highest weight states. So in particular, the CFT vacuum will be invariant under SL2R, whereas if you have a general highest weight state, then that will just be invariant under U1. Okay, so, and then you can do the standard Pfefferman-Graham prescription, and so to calculate the geometry that is dual to your particular CFT. And so the nice thing here is that the Pfefferman-Graham expansion in this low dimension terminates after a finite number of terms. So it stops here, and so you can directly express your higher order terms in terms of the energy momentum tensor at the boundary. Okay, and now the nice thing is that you can define a Berry phase for the conformal transformations. And so that's done by this concept of a co-adjoint orbit. Okay, I have some mathematical discussion. Okay, let me quickly go through this. So if we have a Virasoro group element that acts on a particular gate, or I should say an operator, by the adjoint transformation in this way, and then it acts on a state V. Okay, so that's dual to this operator in the differential geometry sense by the so-called co-adjoint transformation. And so a co-adjoint orbit is the set of states V that's reachable through a co-adjoint transformation on a fixed state. So that's, you pick your representatives, like the P that we had before for entanglement, but now we do the same, not for entanglement, but for conformal symmetry. And then this is your orbit, okay? And if you do this for the Virasoro group, then you just get a Verma module. Okay, then again, this co-adjoint orbit has a symplectic form, and you can define the so-called geometric action, which is where you just integrate over the symplectic form. And then you can write down the co-adjoint orbit for the Virasoro group, which essentially contains this Schwarzian derivative here. I'm going very fast. If it's too fast, please ask me afterwards. Okay. And now the nice thing is, so there's this very nice paper by Oblak, which we benefited a lot from. So then you can actually write down a Virasoro Berry phase, and so you use this general group theory formalism that I had before and just use it for the Virasoro symmetry. So again, we can define a Berry connection. And now the point is we have to take care of the central extension, so there's an extra term which takes care of the central charge. But, so this connection gives rise to a Berry phase as before. And so these Berry phases, they probe the geometry of a particular co-adjoint orbit. And so in particular, if you so this is our orbit. So if I'm sitting here and I apply this co-adjoint transformations, I just go around the circle once. But then since I have this fiber bundle structure, and if I apply the same orbit to states that are outside, the same transformation to the states which are outside this co-adjoint orbit, then if I go around this trajectory, I end at some other place in this fiber. And this difference is then exactly, again, a Berry phase. Okay. Okay. So we also have Berry phases for conformal symmetry. And so then you can actually use this to also construct the gravity dual by using the Pfefferman-Graham construction to in this ADS3 setting. And so there's a very nice connection with the Brown-Eno transformations and, okay, and the Bagnados geometries. And okay, let me skip all this now. I'm done in 1 minute. Here there's a toy example. So again, this is our black hole. Now imagine that you look from one side of the black hole and you look to the other. So you have here a tube, this is your wormhole. I look here and then I see the other end of the wormhole. And then again, I have a non-trivial holonomy. So this is my Berry phase. So if the green is the end of the wormhole which is pointing towards me and the blue is the other end of the wormhole that's over there, then the holonomy is if I walk once around here. And so the upshot of what I want to make that if you do this for a very toy model example, you can do this for a transhumance action, then you just have a U1 symmetry, and then essentially what you get, so actually I should advertise this very beautiful paper where this has already been considered. And so then essentially you get two actions for the boundary values of the functions that determine your transhumance field. And the key point is, so never mind the details, you have one action on the left-hand side and you have one action on the right-hand side. The key point is that this holonomy, this H0, gives a contribution that couples the two things. Okay, so that's again the same that we had before. There's a non-factorization which comes from this holonomy. Okay, it couples the two sides. And so here this is done for this U1 toy example, but now you can also, so again, because of this holonomy, you get this non-factored structure of your Hilbert space, and and you can also do this for the Virasoro Berry phases that I just introduced. So again, you have one Virasoro on the one hand side and one Virasoro on the other side, but because there's this coupling to the holonomy, actually this factored structure is exchanged for a non-factored one. And again, in the context of all these geometric objects that I was telling you. And that means that you can actually write a geometric action in the sense of this co-adjoint orbits that I introduced before, one for the left-hand side and one for the right-hand side. But this holonomy now forces you that the representative of picking a particular orbit has to be the same in the two actions on the left and on the right. So this whole construction actually forces you to introduce a coupling between the two actions on the two boundaries of your wormhole geometry. Okay, so that's actually a very nice feature. All right, so I'm done. Let me just summarize very quickly. So I've shown you that the non-factorization of wormhole Hilbert spaces is due to a non-exact symplectic form that results in a non-zero Berry phase. And so this is a mathematical structure that is also present in quantum mechanics and in conformal field theories. And I think the stuff I was telling you today gives you a really nice relation or new ingredients, new quantitative ingredients for understanding the relation between entanglement and geometry. So that's the relation also to ADS-CFT and why I think this is important. There are new possibilities for doing actually experiments in context to this entanglement orbit. So really we can learn something about ADS-CFT by just looking at the entanglement properties of very simple quantum mechanical systems. And then there's also this beautiful relation to this new development of the von Neumann algebras. Okay, thank you very much for your attention.
Questions?
So I have two questions. One, it means both the questions are related to the fact that vanishing of the Berry phase leads to existence of a trace.
Yes.
So in the quantum mechanical example, I got a feeling that you wrote down the trace in terms of some states, and then you showed that the definition in terms of those states is proportional to the Berry phase. But somehow you could have a definition of trace which is not in terms of inner product of states or something like that, right? So is that particular, maybe I missed something there?
Yeah, let's go back. I mean, of course, you can always, okay, I mean, that's, of course, that's my pick of, I mean, I'm just saying I would like to construct a function which has all the properties I want.
Yeah, yeah.
So I want to construct it in terms of an expected notation value of quantum mechanics, so I can really think of the ground state of this Hamiltonian that I used. So that's what I'm doing, and then I can actually show that this expression takes this form, and from my analysis of the Berry phase, I see that the two are proportional to each other.
But can there not be a definition of trace which is not in terms of expectation value? or maybe in
well, if you have a
quantum-
density matrix, okay, it's a very good question, but I mean the point of having a density matrix is that it's defined on your Hilbert space, and you somehow need the basis of the space. So I would at least say that this is a very natural approach of doing things.
So, and my second question was when you said the claim where the adding 1 by n corrections to the picture leads to you going from type 3 to type 2, and you said that maps directly to some maximal entanglement leading to Berry phase. So I didn't see the connection between.
Okay, yeah, sorry, I was going very fast. Okay, so this is the von Neumann construction, and okay, I mean, you know, I just have an analogy here. Okay, so so the analogy here is now that, okay, so obviously including the 1 over n correction then just means that here you don't have this so you know, U doesn't commute with all the operators anymore. Okay, and that really leads to the same center which you have on the 2 sides. But okay, so our holonomy does something very similar. Sorry. But so here this transition from type 2-3 to type 2, you know, I haven't expressed this in terms of any 1 over n corrections. Okay, I can just say by analogy to what I had before. So if this is the case for the type 3, but I can already see that if I have a maximally entangled state, then in that case the Berry phase will vanish, and so that allows me to actually define a trace for a particular state, namely this one. So that was the logic. Okay. But I agree with you. I mean, okay, it's not at the same level of detailedness and explicitness as I had for the type 1, and certainly we can do more.
Thanks.
Hi, yeah, I was going to ask about the geometry of these entanglement orbits in the quantum mechanics example. So I think for the non-entangled state, you had CP1 times CP1, and then the maximally entangled was RP3.
Yes.
Are those geometrically, is the first a quadric in CP3, the second's the real submanifold of CP3? Is that how they're arising, or it's not?
Yes, I think that's exactly what's happening.
So the first is holomorphic, the second is Lagrangian. Is there any significance to that? And then the mixed one was then mixed complex Lagrangian, like you get in generalized geometry.
Yeah.
Any significance?
It's a super interesting question. I think you were precisely right. In the second example, we get this Lagrangian submanifold, and it would be super interesting to make the connection to the things you were mentioning. But we haven't thought about this yet. But it's an obvious next thing to do.
Okay.
Yeah. Thanks for pointing this out.
So in the Berry phase, I think you consider a 1-parameter family of states, right? And you let them go into a loop, and then you find some non-trivial phase or not.
Yeah.
I didn't really see, or maybe I missed it, like, what curves do you trace out? Do you sort of stay in the same entanglement orbit, or do you go from one to the other? Or
okay,
I mean, what is the precise curves you trace out in
yes,
this,
I was, okay. We do something slightly more abstract, but in the mathematical sense is exactly the same, but it has, the physical interpretation is not as obvious. So the, what we're actually doing is to, where was my general statements? Yeah, this one, sorry. Okay, so you can define this, so I showed you this example where you could say I take an electron in a loop around a magnetic field, but this is a kind of physical example for a more general mathematical structure, and the mathematical structure is based on these Bauer-Cartan forms. So I can just do mathematics. I can just say I pick any group manifold and I take a group element, and for this group element I can define a Berry connection.
That's right, but to compute a phase, you still need to integrate it, right, over some region?
Well, yes. I mean, here, then in that case, if you have a connection, you can also write a curvature, and then we integrate this 2 form in such a way.
That's right, but I was just wondering, in the case you considered, do you sort of keep the entanglement fixed, or do you move the states, like, what kind of regions do you integrate over to get these phases?
Yeah, where was my table? Yeah, this one. Okay, so these orbits, they are precisely that. Okay, so I had these P's and Q's later on. Maybe I should go to the P and Q later on. Yeah. okay, so here again, I have this fiber bundle structure that was talking about later. So I can, this P just fixes me one element of this entanglement orbit, and then I can apply this unitary transformation, which, okay, so because I have only 2 spins, I just have SU2, and so I can use the Pauli matrices. So in this case, everything's very simple. And then this Q is all the points I can reach in this fiber bundle structure, I mean, by applying this particular transformation. And then from this, I define the connection. Yeah, sorry, I think I went very fast over this. And then from this connection, you can, so the symplectic form is then again this curvature. What was the curvature? This curvature, yeah. So this is the same. And then, I just integrate over the curvature. So it's the same, so I integrate over theta and phi again. Okay, and then I get this expression.
So you integrate over what, precisely?
I integrate over theta and phi, but I integrate over this 2 form, which is the symplectic form. So, but I mean, you can, for the simple case of the magnetic field, and you can show that this is equivalent. Yeah.
I'm asking because, I mean, in computing these Berry phases, I think there are different interpretations depending on what kind of changes you do to the state, right?
Yes, exactly.
I mean, some of them have interpretations in terms of, in holography, of moving like things around, or if keeping things fixed and changing the global state.
Yeah, I mean, here I'm using this very abstract definition. I'm just saying I move in a particular orbit in the sense of differential geometry.
Yeah. Okay. Well, anyway,
we can talk about this later.
Well.
Yeah.
Okay, I think we can thank Johanna for a nice talk.
Thanks.